on a full visiting tour as a student. So as I said, I hope the talk is not too low level for you. It's a review talk, but it also contains in this section here new results, which are still preliminary, but the paper is almost finally written and will come out, I think, in the next month on the new global determination of nuclear parton distribution functions. But as I said, I will try to give a more general overview based on a large review article that I wrote with our competitors, Hannu Paukkunen from the EPPS collaboration in Jyväskylä, and I'm also representing the NCTEC collaboration with several many different members. And show you how how much progress has been made on our knowledge of nuclear parton distribution functions. So this is all about collinear parton distribution functions in just the longitudinal and momentum direction. As you know, the EIC program will, of course, address a more tomographic picture of the nucleus in 3 dimensions, hopefully in the future. Okay, so the nuclear structure. I mean, nuclear structure can mean many things, of course. Also here, when we talk about nuclear structure, it means nuclear structure at high energies and at the quark and gluon level, and how the quark and gluon distributions change when a nucleon, a proton, or a neutron is not free but bound in a nucleus, and what that tells us about the nuclear dynamics. That's, of course, a very important question, because nuclear structure is an emergent phenomenon from QCD. But it's also important because at some point we also want to understand how deconfinement happens in the initial state in the phase transition in heavy ion collisions. And that's, of course, also an important question. It will probably not be answered by collinear PDFs alone, but that's an important boundary condition, and this will help us to understand this equilibration and finally the deconfinement and the creation of the quark-gluon plasma. So our work is, or our understanding is based on QCD, and of course QCD is a very complex theory with some things that you can actually calculate and some things that you can't. In particular, in perturbation theory, we know that we can calculate the evolution in the virtuality Q squared, or in the energy or resolution scale of these parton distribution functions F, which is this a pointer actually, or
there's a mechanical pointer behind you.
Okay. Yes. All right. So the parton distribution functions of quarks and gluons, probability distribution functions are usually denoted as a function of the longitudinal momentum fraction x, and the energy scale or resolution scale Q squared, and the evolution in Q squared is governed by a perturbation theory and calculable with these famous D-Glob equations. This can be done at next leading order or even n cubed and alone nowadays, although I will get to the question of precision in a minute. While the dependence on x is actually not calculable in perturbation theory, we know that these PDFs should be universal objects because we have this QCD factorization theorem, which is at least for some processes proven, and at least for protons, although there are some caveats with respect to nuclei and with respect to other processes other than deep elastic scattering and Young. So since we can't calculate these dependencies on the longitudinal momentum fraction, what we usually do is we fit these distributions to experimental data. We calculate the hard scattering processes in perturbation theory. We compare our predictions as a function of these PDFs to experimental data, and then relying on the universality of these PDFs, we fit them to experimental data. And so, what we then obtain are PDFs of protons and neutrons bound in nuclei when we look at scattering on nuclei, which differ from those in free protons and neutrons. And we can parameterize these differences in a model agnostic way. This is what most people do in this business, just to determine the modifications, but you can also take the alternative route and putting in models, nuclear models. So as there's a famous Coulagin-Petty model, for example, where you put in different physical effects in different regions of X. So the business started, well, like almost everything in this business here in California, with deep inelastic scattering. So of charged leptons on nucleons or nuclei, initially, of course, in fixed target experiments. Then with Hera, this was also done in colliders, and in the future, this will also be done at the EIC on nuclei. But this is not the only process. So in addition to photon exchange at low Q squared, at higher Q squared, you also have weak processes that we've already briefly talked about. There's also neutrino scattering or charged current scattering in general. You also have charged current scattering at Hera, for example, when you have electrons going to neutrinos. But neutrino scattering, where you create neutrino beams, for example, at Fermi lab and scatter them again on fixed targets. And these processes are completely inclusive. Inclusive deep inelastic scattering, you just measure the outgoing lepton, and the hadronic state is summed over. But there are also more or less inclusive processes. For example, in neutrino scattering, there's the important process of dimuon, so-called dimuon production, where one muon comes from the charged current on the neutrino line, and the other muon comes from the creation of a charm quark, decaying to a muon plus other stuff, which is particularly important because it's sensitive to the strange quark density, one of the lesser known parton distribution functions. And so, these are the most abundant data for a large variety of nuclei, because you can easily exchange them in your fixed target. In a collider, that's more difficult because that depends on the machine parameters. And there are also important effects that you have to consider more in nuclei, so-called higher twist effects in the operator product expansion. Because these are usually more important, as John Ray Chu has shown, and as is also sketched diagrammatically here in these diagrams. They are more important for larger nuclei than for protons. They come from transverse size effects, jet mass effects, rescattering effects, and they scale with higher suppression factors, power suppressions in Q squared. And they're expected to be enhanced in nuclear collisions by the nuclear mass to the 1/3 power, because there are many more soft partons flying around. So in general, it's a problem if you have low Q squared data in nuclear collisions to disentangle initial state effects, which would be representative of nuclear modifications or parton distributions, from final state effects, as you would expect them from jet quenching, for example, and which, of course, are other physical effects that you would like to distinguish. So this is a very famous plot from the EPBS coloration, schematically showing what different effects there are. The EPBS people, they factorize actually the nuclear dependence into free proton PDFs and the nuclear modification factor, but you don't have to do that, and in CTEC we actually don't. We parameterize the nuclear dependence directly in the parton distribution functions themselves. And these effects can be categorized into 4 different regions as a function of X. Here, this is the ratio of the nuclear PDFs per nucleon divided by the free PDFs. And going from low X to high X, you have the famous effects of shadowing, a suppression at low X, where the PDFs are smaller than, or this ratio is smaller than 1. And in all of these effects, or in many of them, you always have this competition of either a partonic interpretation versus a nuclear interpretation. And it's one of the goals of this business to actually decide what's actually happening physically. And so shadowing, for example, as we have also just discussed, in a partonic picture can be seen as the absorption of a QQ bar dipole, which is generated by the weak boson that scatters on the nucleus, and which is absorbed by surface nucleons, and therefore these cast a shadow on the probe's nucleon, and therefore you get this suppression. And then on the other hand, at large X, you have again a suppression, which is the famous EMC effect, but that's a very different physical process, or believed to be a very different physical process. in the valence region, because there the valence quarks participate or probably participate actively in the nuclear binding. Again, you can also see this in terms of a hadronic picture with pion exchanges or quark clusters. There may be an effect of correlated nucleons there, as I'll briefly touch on in the conclusion. At very high X, you have Fermi motion. These PDFs in principle can go also above X, because X is the longitudinal dimension fraction per nucleon, and since the nucleon can get a push from the other nucleons, this can go above 1. But yeah, so this you describe these nuclear PDF or structure functions as a convolution of the nucleon structure function and the nuclear motion, and this gives you this increase here at large X, and the least understood region is probably the anti-shadowing region, which we also already talked about, because there we don't really have a clear physical picture of what's happening. One idea is that this might just be caused by local momentum conservation, and in total, of course, it is imposed by the momentum sum rule on the PDFs. But that may be even the case locally.
I have a short question.
Sure.
So this shadowing can be calculated by the CGC framework? The shadowing region can be calculated by
the color glass condensate framework. Well, in principle, there's a connection, but yes. So yeah. But it's not a one-to-one correspondence. So yeah. Let me get back to this point later. Okay. Okay, so the structure functions, which are related to the measured cross sections, are a convolution of these non-perturbative objects, the PDFs, with the partonic Wilson coefficients, and so these are calculated at some order in perturbation theory. One can separate just technically these nuclear PDFs for a full nucleus characterized by mass and charge, although usually we don't really distinguish the charge yet because we are not yet sensitive to QED effects. That's another important caveat. You can decompose them into bound proton and neutron PDFs, which are not really physical objects, by just separating them with the corresponding numbers of protons and neutrons in the nucleus. But this is just a technical aid to sort of understand what's happening. The evolution equations are, again, convolutions of these non-perturbative objects with ultra-radical VC splitting functions, which are also known to very high order nowadays. And on top of that, we usually impose sum rules for different, momentum sum rule or valence quark number sum rules, etc. And isospin symmetry between up quarks and protons and down quarks and neutrons. There one also has to be a bit careful. There has been some confusion recently in discussions with Melnichuk on what is exactly meant by this. You have to exchange also, of course, the number or weigh this with the corresponding number of neutrons and protons. Otherwise, you're actually not doing the right thing. Yeah.
So if you take a model of a nucleus, heavy nucleus,
yes,
there's a neutron skin.
Yeah.
So the spatial distribution of protons and neutrons is different.
Yes.
And one might just very naively expect, nucleons on the outside of the nucleus see less shadowing than those in the middle.
Yes.
So what does that say for this isospin symmetry argument?
Well, this is a problem that I think will have to be addressed when we go to the three-dimensional structure of the nucleus, right? Because what you're alluding to is a geometric difference, and we're working in momentum space, so we cannot directly do a one-to-one correspondence here. You can probably relate it by a Fourier transform, but I think you would need nobody has done it so far, I would say. It's an important point. Maybe you can even already do it in one dimension with the Fourier transform. So one might try it, but we haven't done it.
I mean, even if you integrate over Z and you split down to a flat nucleus, you still have neutrons around.
Yes. Right. Yeah. Mm-hmm.
Just to confirm, the Q square on the left is the physical
Q
square,
that's
and
right.
on the right hand side, it's more like a choice of the scale where mu is set to q squared.
Yeah, right.
Okay.
Usually it's identified if you only have a single scale in the process, but you have some choice there.
Okay.
Right. Mhm.
Sorry, one question to clarify. So on the previous slide, you mentioned that looking at the modified proton and neutron distributions in nuclei, and then at the bottom you have the Fermi motion separate. So on the next slide, when you talk about the nucleon distributions, well, so this doesn't have that smearing. So
No, well, actually the smearing is just technically it's implemented by a shift in the x variable. So with an epsilon. So you can actually approximate this convolution integral by a small shift in x or at high x.
So I guess I just want you doing that as a separate step, or when you show the F2 for the proton in the nucleus, does that already include?
That already includes the convolution. Yeah.
So back to that diagram, a question. You can talk about it forever. So you talk about anti-shadowing and say it may just be some kinematic consequence of momentum sum rule, but the momentum sum rule is over the entire scale.
Yes.
So it may also drive, there can be some dynamics in the shadowing, but it also may just be a kinematic constraint.
Yeah.
I mean, I was trying to invent some toy model in my head. I'm not going to succeed, but let's imagine, that the driving physics is Fermi motion and two-particle correlations. In other words, a very high x.
Yeah.
Then everything else is just a tail that's kind of flapping away, and there's no particular driving dynamics. It's just the momentum sum rule that dictates, what you need to have there in order to add up to one. So yeah, maybe that means that everything's correlated with everything. So trying to understand the dynamics of shadowing independently is kind of, you're not going to get there quantitatively. Is that?
No. Again, this approach that I mentioned by basically Vadim Bouze and Strickmann, this is a model. So basically you ask for local momentum conservation, not just a global momentum sum rule. But there's no real proof in experimental data for that. So, Right. Okay, so this is an overview table of the state of the art as of late 23. The first three columns here are the global fit collaborations. And well, as I said, I represent NCTEC, then there is the Eulascular group from Escobar and company, and then there is the nuclear branch of the neural network collaboration. And they differ in their Ansätze. For example, as I said, EPPS uses this factorized Ansatz, NNPDF doesn't use a parameterized form at the starting scale, but actually uses a neural network to model the X dependence. The heavy quark schemes are different, the number of data points included are different. But when I say global fits, it basically means that these three collaborations include a large fraction of the LHC run 1 and some run 2 data. They are all at next to leading order in QCD. There are two collaborations that have tried to go beyond that, to next to leading order, where the perturbative ingredients are available for at least the deep elastic scattering and the Young process, but not all of the LHC processes, at least not in a rapid numerical form. And that's why you see very, very little check marks here in this region. So Tutu is Werner Vogelsang, basically, and Ilka Helenius, and KSASG is Kanpur, an Iranian guy that has been collaborated with some other people, Vadim, for example. And so I will mostly show only comparisons of the three global fits, because the LHC data, and that's the focus of the talk, and they have a big impact on the nuclear PDFs. There are a lot of other technical differences which would take too long to go into detail. If you have more questions, I'd be happy to explain what the different assumptions are in the different global fits.
So what systems are they measuring at the LHC? Is this proton nucleus? Or?
Yeah, it's always proton nucleus. In principle, you could also use electroweak-boson production from nucleus scattering, if you assume that there are no medium effects in this process. And there's no final hadronic final state if you take a electronic decay of the Z boson. But okay, so far this has not been used in these fields.
So this is mostly ALICE, CMS, and so on.
It's all for LHC collaborations, it's only it's actually only proton-lead.
Okay.
Right. And now we have some xenon data, and there will be some oxygen data, and then there's the nice LHCb fixed target. What's the name? SMOG program. So that will give us a lot of variety of nuclei again. Yeah.
So how close are you to using ultra-peripheral collision
Yes,
data?
excellent question. Very close. I mean, the difficulty is that ultra-peripheral collisions in principle probe different quantities. They probe generalized parton distribution functions, which also depend on the skewness of the two partons that go into the process. Yes, for vector mesons. But it has been shown that you can include the skewness only in the last step of the evolution in the perturbative way, so then you can relate these GPDs again to the normal PDFs. And so, well, there's an NLO code by Chris Flett, which can be used. So it will not yet be in our NCTEC 25 book, but it's on the list as one of the next processes because it's quadratically sensitive to the gluon distribution because there are two gluons going through, so it's very, very sensitive. And we've been people have pushed us very hard for a long time to use these data. I think I will show one comparison.
You didn't say explicitly, but I'm assuming the goal is to extract nuclear effects in an absolute sense.
Mm-hmm.
Yet the protons, the baseline proton PDFs differ between these models.
Yes, yeah, another very important point.
So how different are they? How does that affect that?
They are different. In particular, we always stress the fact that our competitors use proton PDFs that include some nuclear data, in particular for flavor discrimination and the neutrino scattering on the strange quark. And so our approach has always been to take a nuclear-free proton baseline in order to avoid double counting effects. And that's why you see here this very old baseline CTEC 6.1 and a tilde, because that is a fit that Jeff Owens has made. It's a refit of CTEC 6 without nuclear data. And recently, we'll get to that in a minute, we have been using the CJ fits from the Jefferson Lab people. These also do not include nuclear data apart from deuteron, and then they have a special treatment of deuteron corrections. And the deuteron is a very special nucleus, so it's not included in our nuclear PDFs, but it's treated differently because it's very lightly, very weakly bound. But indeed, this is a problem because the nuclear-free baselines, they have less constraints, obviously, than on the strange quark, for example. And in general, usually use a smaller database than the other global proton fits. And so it's very important, and that's one of the reasons why I'm going to INT next week to discuss with Pavel Nadolski. They are working on a CT25 release of their proton PDFs, which is a global proton fit, one of the three major ones. And hopefully we will also, we're now using CJ22, which is already much more modern, but a CT25 without nuclear data would be probably a very good way to go. Yeah, very important point. You do not want to double count the effects. So yes.
These all nucleus are unpolarized.
Yes, these are all unpolarized nuclei. Yeah. I think people have not looked at polarized nuclear PDFs so far. There's certainly no data. Right. Yeah. Okay, so I stressed that the global fitters have stayed at next to leading order so far. So the precision of the data so far has justified that because they were much less precise than the proton PDFs, where we have this wealth of Hera data and also lots of LHCP data. And so NLO and even higher orders are clearly required. Now, for nuclear physics, this is changing. So in some first processes, we can see the effects of NLO already. And so we will have to go to NNO also in the future. But so far, the data have been not so precise, so NNO was okay. The bottleneck is the fast evaluation of the codes for deep elastic scattering. This is an inclusive process, and so you can directly fit your data to the predictions. For hadronic processes, this is takes much longer, and therefore you have to actually grid the NNO calculations to make them sufficiently fast for the iterative fitting of the PDX. And there's a number of tools here available. The most modern tool that we are using now and also helping to develop is Pineapple, which actually allows for multidimensional grids in X and Q squared, and even in Z for fragmentation functions if you have final states for like hadrons where you have another convolution variable. So that's the state of the art where we will go. And so this is important for all LHC processes. The heavy quark treatment is a technicality which maybe is not so important to dive into. There are basically two different approaches how to match massless calculations which are valid at high transverse momentum to massive calculations which are more valid at threshold. You have again to subtract the overlap to get a continuous description. And we of course use the SACOT scheme because we had all this is on our collaboration.
Do you also use Drell-Yan and non-neutrino to probe the antiparticles?
Yes,
or
right.
that's
Drell-Yan, you're absolutely right. The Drell-Yan the process is most sensitive to the anti-quarks. Yeah. Mm-hmm. Exactly. Yeah. Deep elastic scattering is mostly sensitive to the quarks, particularly valence quarks, and Drell-Yan to anti-quarks. Neutrino scattering on the strange quark, and then you need something to constrain the gluon. And this is, well, in the past this was some RIC data, for example, on inclusive pion production, and nowadays it's LHC data basically. And one of our distinguishing features is that we also use heavy quarkonium data. Heavy quarkonia, you may know, are a tricky issue because the binding and the production is not quite clear. Well, Ramona Vogt, I think, is well known here in these areas, and she's been working on the color evaporation model, which relates quarkonium production to open heavy quark production, but doesn't have a clear theoretical basis, contrary to the effective field theory of non-relativistic QCD, which is developed by Godwin, Braffin, and Lepage. But even NRQCD has its problems with issues of factorization breaking at next to next reading order, etc. So, and the problems that you have when you try to globally fit the transition matrix elements. But nevertheless, there's a phenomenological way how to include quarkonium production, and they are very valuable not only in exclusive processes but also in inclusive processes, because ALICE in particular has a lot of very precise quarkonium data, and they are sensitive to the gluon. Okay, I don't know how much time I have at this speed. I think I will take longer than an hour.
So maybe we should reduce the questions to only essential.
I'm happy to answer all the questions,
yes.
Of course.
Then we can do over here.
Go longer, I think.
I'm very happy. As I said, I was at CERN in January for the heavy ion coffee, and there people grilled me after the first two sentences, and it took for 2.5 hours. So we can do this here as well if you like.
The reservations is 5:45, so there's a hard cutoff.
Yeah, right. Okay, but I'm going here step by step. So before I get to the LHC data, I'll briefly mention the traditional basis, in particular deep elastic scattering data, which are here indicated in the X and Q squared plane in blue. These are the fixed target data points from NMC, for example, or stack data, etc., that have been traditionally used, quite old data that have already been used in the NCTEC 15 fit. Then in green, we have the Drell-Yan data, as we discussed, important for the antiquarks. But now recently, this topic has been revived with the JLab measurements a very precise high luminosity measurements Jefferson lab with a 6 GeV electron beam. And the peculiarity of these data is that they extend to very high X. So these are these yellow points, and traditionally these data points have been excluded from the fit by cuts on X on Q squared, the virtuality, and W squared, the hadronic mass, which have to be sufficiently large to ensure that you're in the perturbative region and that you don't have any higher twist effects. But it's a pity to throw away all these data, so it's better to think a bit harder about the theoretical corrections you have to do there. You can see how much more precise these data are here in the high X region. So this is the EMC effect region with the suppression and then the Fermi motion. And you can see that they are orders of magnitude more precise than the older data. And so we did a specialized fit to these data, including the 3 different types of corrections that you have to watch out for. One is the deuteron corrections, as I mentioned, it's a loosely bound particle. And yeah, we follow the Jefferson lab or CJ collaboration in accounting for this deuteron binding. So Fermi motion, nuclear binding, and offset effects. The second effect are target mass corrections. So because the ratio of the mass over Q squared may not be small in this region, so the X variable has to be shifted to the so-called Nachtmann variable. And the third type of correction is higher twist corrections. You can see higher twist because it's a suppression by 1 over Q squared. You can see the nuclear enhancement by A to the 1/3. And then you can take 2 different approaches to these higher twist corrections. Either you take them multiplicatively on the leading twist, or you take them into account in an additive way. So far, we have only done the multiplicative, but other people have done checked both options. So once you account for these, and we have also written a review on higher twist effects in nuclear collisions, if you're interested in the details. Yeah.
Just for a quick question/comment. So I don't know if you're including the class data on nuclei in these fits.
We are.
But we looked back at the radiative corrections that were used there and found that a difference in radiative corrections was the reason that there was sort of a consistent disagreement with other worlds' data.
Okay.
So we have a paper with updated versions of the data after those corrections.
I see. Okay. From when is that paper?
Last year.
Last year. Okay. Yeah. So I'll make sure that when we include these data in our global fit, that we take the correct data.
Well, this was a separate analysis. The person who did the original analysis worked with us on it. Okay. I'm not sure how the class collaboration feels.
I see. Okay.
I think they would agree, but
I see.
Just to warn you.
Yeah. All right. Thank you. I have to make a mental note. Yeah. So yeah, these fixed target data usually, well, okay, one can say a lot about this in the neutrino context, in particular about small collaborations and etc. Anyway, so yeah, we're getting into the neutrino DIS data now. So this is second type of deep elastic scattering, now in charge current. And there has been a long-standing discussion whether these data are compatible with the neutral current data. Papers being written back and forth, in particular between us and the EPPS people, who did some tricks to try to make them consistent, take out the correlations of the systematic errors, normalize per bin and tricks like that, which made them consistent. And they also have another proton baseline. They have the CT18, which includes actually neutrino data. So maybe it's no surprise that it came out consistent, whereas we didn't. So with Hanu, when we wrote the review, we had to find a compromise, a consolidated perspective. So basically, the conclusion is that there is a lot still tension with the UTEF data in particular. The problem is that these are very many data points and they are nominally very precise, and that's why they usually give a huge chi-square when you fit them together with neutral current. You just cannot get a consistent fit. It's impossible. And so in the end, we are not the only ones, NNPDF pretty much do the same. We concluded that we cannot use the inclusive DIS, neutrino DIS data. We only use the chorus data and we use the dimuon data. The dimuon data is less inclusive and has more constraints on the experimental quantities that you have to determine. And so we think that's more reliable. yeah, so and there's also the question of electroweak corrections and what exactly the calibrations publish. We shouldn't use the structure functions because again, they have a theoretical translation in them. You should directly use the cross sections. They are more reliable, etc. But the problem is that they are really important because they are the ones that are sensitive to the strange quark. And there is, of course, the interesting question whether the nuclear effects are the same in charged current and in neutral current. Okay, so that's about the fixed target sector. If you look at the global kinematic plane here in X and Q squared, you can see that these data mostly sit, of course, in the high X region. So neutral current in red, charged current in blue, Drell-Young PA fixed target in green. And then you see the game changer. You see the LHC data, which cover a much wider range now in this plane, both in X going down to 10 to the minus 5 now instead of just 10 to the minus 3 or 2. And also very high Q squared, in particular for jets or photons. But there's also first measurements on top quark production, for example, as I'll show in a minute. So clearly you get a much bigger handle, in particular in the low X region and on the evolution from the LHC data. So following more or less the measurements and the development of the technicalities in the fitting programs, we started, or most of us started by including the weak boson data, W and Z. The intention was, of course, that these might also be sensitive to the strange quark, because again, and C quarks, of course, also. And this is the list of data that are available now from run 1 and run 2. And I added here, so the black check marks are from the review, and I added in red the measurements that we have now added also in NCTEC 25. So basically it includes also all of the available run 2 electroweak-boson data. And so here this is...
Actually, can I ask about the, generally about the procedure? So let me go back. Now, some CMS, Z measurement, there's a paper, there's error bars. But as was discussed earlier, one also needs kind of covariances. And is there some kind of additional input about the nature of experimental data that you need to assume something about covariance lengths and so on in order to do these fits? And if so, is that done consistently across the various fits?
Yeah, okay. So correlated systematics in an experiment are usually taken into account. Among experiments, different experiments at the LHC, that's a very different issue. Mainly Cooper-Sarkar, I think, has tried to make global analysis trying to correlate.
Sorry, but even within experiments, understand the correlations.
Yeah.
It's an incomplete art.
Yeah, sure. Well, we take what we get basically, and sometimes
they're not reported either.
Yeah, right. So, for example, in the NUTEF data, they are only in some appendix, not in the paper actually. So the correlated errors, you have to really look for them. With modern collaborations, I think this should be understood that you should, as carefully as you can, publish the correlated.
So broadly, at least in modern fits, or is this done consistently across the various fitting groups? Or? Yeah,
this is, I think, we more or less do everybody does the same thing. We take what is published in terms of correlated systematic errors from the LHC. Yeah. But this has been less problematic than for the neutrinos in general. One thing which is important for the LHC is that we now shift the normalization of the data normally, and that's justified because of the luminosity uncertainty. So and that's taken into account in the chi-square determination. Okay, so this is the W bosons from CMS. I think this is the run 2 data, 8TeV. You can see how the different fits fare. These are the 3 global fits, EPPS in blue, our fit in red, and NNPDF in green. This is the usual color coding all over the review. And And in black, you see if there are no nuclear effects apart from the isospin, because the lead ion has many more neutrons than protons, and you can clearly see nuclear effects here in the forward region. And yeah, you can also see that the three global filters more or less agree with the description of the data. There are some technical differences. We fit absolute cross sections. The PPS fits ratios, which fits their philosophy of actually a nuclear modification factor. And what you would think is that the W has particular sensitivity to the strange quark, but since you're now producing a high Q-squared particle, the strange is actually produced by the evolution from the gluon splitting. So you're actually almost equally sensitive to the gluon and not so much to the strange quark as you would have hoped. So that's why, for example, W plus charm production would be another important process, because that would be directly sensitive to the strange quark. We haven't fitted that yet, but it's also on the list. And that would maybe be able to replace the neutrino data. So Z-boson production, again, run 2 from CMS is very precise now, and this is a plot which shows you now for the first time the impact of next to leading order corrections. So here, let me see. Yeah, this is the ratio to next to leading order. So you can see that the data here in the low mass region, so 15 to 60 GeV, are clearly above the NLO prediction, and you need next to leading order to describe the data. There is a problem in the forward-backward asymmetry, as you can see from this jump here. So this data is actually very difficult to describe, even at next to leading order. So there may be a question about the reliability of the experimental result there. Yeah, so low mass, I think I've discussed that. Prompt photon production, a topic very dear to some people's hearts in this room, has, this is the Atlas measurement at high transverse momenta. So this is 100 GeV, so basically from 30 GeV or 25 or so up to several hundred GeV, which is the specialty, of course, of the search or general purpose experiments, like Higgs to diphotons, for example, needs these high PT photons. So this is the data that has been included in NNN PDF, but not by the other collaborations. And you can see a fair description, but not a very big impact because the error bars are still relatively large. And so there's also maybe, it's not quite significant yet, an indication that you might need next to leading order. This is the plot that I was alluding to just a minute ago. The ALICE measurement, which has more sensitivity down to low PT, which might be more interesting for nuclear PDFs because that's the low X region where you expect to see shadowing, so a suppression ratio of nuclear to proton below 1. You can. I used actually the preliminary plot and not the published plot here because it has all the information in one plot. So it has actually the comparison and consistency with the Atlas data shown here in red. It has also the predictions on the same plot by the 3 PDF fitters, which within the error bars are all consistent. And again, of course, one should include these data, but the pull, in particular, if you include the systematic errors, is not that large.
That actually went down in the final result. So
okay.
It's about we call it a 2 sigma effect.
Okay, good, very good. And I think this point also went down.
The error bar shrank.
Yeah, right. But the difference that I noted was that the last point here went down a bit. So, but it has a large error bar. Anyway, so ALICE has sensitivity. Our gluons are here a bit. And ALICE focal, the new forward calorimeter will cover the forward region, so that will also, of course, be very interesting for low X physics. And you all know that Florian Jonas who did this measurement, is a student from Münster who is now a postdoc here at Berkeley with Peter. Okay, that's the photons, single inclusive hadrons. So this is the process that was first used to determine the gluon from Rick, for example, but also At the LHC, you can see that this red area here, which describes the contribution of gluons to the scattering process, is quite large, above 60% of a large region in transverse momentum. So this is very important, or was very important, to constrain the gluon. The drawback is that if you produce hadronic final states, you have to describe the hadronization. So the quarks and gluons fragment into a hadron. And so you have to decide which fragmentation functions you want to use. We decided for the DSS set because they have uncertainties that we could include. We use pions and kaons. The eta mesons don't have a big impact. They have been measured, but there are also no uncertainties on the fragmentation functions. And then next to leading order, for such a hadronic process, you usually have relatively large scale uncertainties, meaning that your perturbative prediction is not so reliable at this order. But in this nuclear business, we have the advantage that we always have a proton baseline. So we can actually fit the scales to the proton-proton scattering process. And then we fit the nuclear PDFs with this choice of scales. And that, of course, eliminates most of the uncertainty. So that's sort of equivalent to taking ratios like EPPS does, but a different approach.
Yeah. PT is a hadron level PT?
Yes, this is the hadron level PT. Here is what I mentioned about the luminosity uncertainty. So that's how we refer to normalization, because the luminosity allows for a few percent, even in 1-2, uncertainty on the normalization of the data. Digit production, CMS, has been used by the EPPS collaboration. Here, the problem is that in nuclear collisions, even PA collisions, you don't have just one hot scattering, but you have several. So an average, like David Dentaria has shown, we have 7 ± 5, which is, of course, large uncertainty, interactions which you can model with the Glauber model. And so you have to sort of subtract multi-parton interactions and go to sufficiently large transverse momentum and small jet size to reduce uncertainty. And so here this shows the impact on basically the jet data is what's mostly constraining the gluon in the EPPS fit, because they have much less heavy quark data, which we use. And they have taken the pain to also include the uncertainty from the underlying proton. So the blue arrow band here shows the nuclear uncertainty, which is particularly large, well, in the small x region or forward region, while the underlying proton PDF uncertainty is large in the backward region, where you're at small x for the proton. And of course, in the future, one should include both uncertainties, those on the underlying proton and those on the nucleus, in a correlated way. So the big step forward that we took 2 years ago on the gluon distribution was to include the wealth of the heavy quark and quark-helium data, and I have to say that this was mostly due to the initiative of Peter Braun-Munzing and Johanna Stachel, who had a project with us in the Heidelberg SFB, and that gave us the manpower to do that. And so because of the theoretical issues with the non-relativistic QCD and the hadronization of the quark-helium, we use a data-driven approach where the matrix element of the hard process and the hadronization of the quark-helium are fit or modeled by this crystal ball function. And this is modeled in PP, or the parameters of this function are determined in proton-proton, so that then after you have determined them, you can again use these processes to fit the nuclear PDFs. We did one modification to this parameterization, which was to include a rapidity dependence, and this was due to the fact that LHCb has this forward geometry, and it's impossible to fit LHCb data without this rapidity dependence. And they are very important because they are very sensitive to low X gluons, and they are very precise. Yeah, so, okay, this is technical stuff, how we determine these parameters. This is the result of these parameters for different particles, d mesons, shape psi, epsilon, psi prime, and so on. And yeah, we show that our determination of the parameters is consistent with the NRQCD prediction for the quarkonia and with the perturbative prediction for heavy quarks. So this is just a control plots that what we are doing is makes sense also in perturbative QCD. And so there's a lot of data. So the heavy quark data are all the data here on the left. So basically, yeah, right. Up to here, these are all quarkonium and heavy quark data. And yeah, so this is a comparison, for example, for D-meson production, and you can see the description of our fit in
So what's the upper plot? It's chi-squared or?
these are the chi-squareds per data set, actually. So this is one per data set and data point.
The heavy quark is always below 1.
Yeah, the heavy quarks are always below 1, except for one data set, which I cannot. I think this can see exactly what this. These are only 2 data points, so this must be Ali's data. I think a central Ali's data set.
Some are far below 1.
Yeah, this is the psi prime actually here. So the inclusive open heavy quark data, but similarly the inclusive quarkonium data are very well described in our fit. And this plot here shows you the exclusive one that one of you was mentioning. So the rapidity dependence, which is quadratically sensitive. So this is lead ultra-peripheral going to J psi with rapidity gaps. And so this is basically double gluon scattering. And yeah, so within the error bars, the data sets are consistent, but there's much more constraining power that would be really useful to include these data in the future.
What's the peak at about jump at around 4.5?
This one here?
No, at 4.
Here.
In the theory in the NC 1015.
This thing. Oh.
Yeah.
Good question. Yeah, that's I don't know. Yeah, I don't know. Yeah, yeah. So yeah, I think this. Yeah, I would have to check. Okay, sorry.
So I don't know if you can talk about hadronization uncertainties. This forward-backward ratio seems to be nice.
Yeah.
In that it's probably less sensitive or insensitive to hadronization
Yes,
uncertainties.
yeah, right. Yes, exactly.
That's why you do it.
Yeah. Yeah. Thank you for pointing out that detail. Right. So these are the quarkonium data. I think I added here in red that we now in NCDEC 25 include also all the other available inclusive data, which were not included yet at the time of the review. And so this is the summary slide from the review, comparing the different PDFs. And yeah, so these are ratios of bound nucleus or bound nucleons versus free nucleons for different flavors, up, down, U-bar, D-bar, strange, and gluon. And what you can see is that the up and down quarks, in particular in the valence region, are very well constrained and consistent among the different groups. That the NNPDF approach goes haywire sometimes with very large fluctuations because it's not parametrically fixed. And then that the strange quark is the most poorly determined quantity, obviously. And that the gluon distribution now is very well constrained down to 10 to the minus 5 in particular in our fit, which includes the heavy quark and quarkonium data. So after the review, the first TT bar measurement came out from, well, not the first one, but a more precise one. There was already a CMS measurement in run 2 before. And then Atlas compared their measurement from run 2 to the different PDFs. And so you can see that our fit and also the Tutu fit, they align exactly with the experimental cross-section. Also, our error bar aligns with theirs. The Tutu is smaller because they are next to leading order, and the others are a bit on the high side. So, okay, these are not very many data points, but they will also be included in the future, of course, in the fit. So, yeah, you have to tell me how much more time I have, if I have time.
Another 15 minutes, how about that?
I have another 15 minutes? Okay, that's great. So I think you want to hear about our new consolidated global fit. So yeah, we've done quite a big number of improvements versus over the old 10-year-old fit. So the proton baseline at the time was already quite old, but we took care to take out the nuclear data. The cuts were conservative, so the number of data points was small, and yeah, we had a particular ansatz at the starting scale which enforced positivity of some parameters. And because of the small number of data points, we also had to restrict the number of fit parameters that we could open up. Now this has changed dramatically. We have now a much more modern proton baseline from the CJ collaboration with the, yeah, again, without any nuclear data. We have extended our kinematic range to include in particular the precise JLab data. So the number of data points is now a factor of 5 larger, and that's of course due to this JLab and LHC data. We've returned to a more traditional ansatz at the starting scale for low and high X. We have included now the A dependence also in a more traditional way because it's known from the old NMC data that the leading A dependence is logarithmic in A. But there's also sometimes sensitivity to the log squared term, not in all cases, but sometimes there is. This large number of data points now allows us to open up almost twice the number of free parameters, in particular for the strange quark, and the tolerance is calculated accordingly. And so this is a plot that my new PhD student Katrin Greve made, which shows you very nicely how the data points evolve over time. So not much has happened in fixed target Drell-Young over the years, of course, but in DIS, there's all this JLab data now. And then we have in particular the LHC data, and in particular for the heavy quark sector. So, and this shows the breakdown per nucleus. So the majority of the points is, of course, from the LHC. And it's very urgent to also have other nuclei from the collider. This is the chi-square per experiment, per type of experiment here. For once the total number, showing the importance of the different data sets, and then also per data point, showing the fit quality per data set, which is globally very good, which is still not quite satisfactory for the neutrino data as expected. And the total chi-square is just below 1, so showing a good fit quality and no overfitting. And then a number of comparisons. So when we compare with the old NCTEC 15 on this scale for the valence quarks, basically this was already well determined from the DIS, the fixed target DIS data at the time. The big difference is, of course, on the gluon density, which is much more precise now. And in contrast, the strange quark density has now a larger uncertainty, but that's because we open up the parameters, whereas previously they have just been identified with the down and up quark, with the down quark C. But they come out nevertheless pretty much. So the guess was actually not too bad at the time. This is our dedicated high X fit to the JLab data. So here you can see that there is a change in the high X region from the JLab data. Whereas, yeah, okay, the other, the high X data themselves, of course, have little sensitivity to the gluon, so they have a much larger error band on the gluon, for example. This is the comparison with the HQ fit, which now it's the opposite. Now we are very close to the HQ fit because they dominate the uncertainty at low X. And the HQ fit did not have any neutrino data, so the strange quark uncertainty has now shrunk with respect to the HQ fit. These are chi-squared scans. Maybe I should not over stress your patients. Yeah, in many cases, it's one particular type of process that constrains the parameters. So this is, for example, the U-valence parameter, which is obviously constrained by the deep elastic scattering data, D-valence as well. The strange quark is mostly determined by the neutrino data, the dimuon data in our case, as expected. And the gluon is constrained by the quarkonium data on one side, and by the WZ data, as I explained earlier on the other side of the parabola. And they all have a very much parabolic shape.
So the D doesn't contribute much, very flat.
The D mesons,
Yes.
yeah, it's much flatter than the quarkonia. Yeah,
That's very,
well, not much, but somewhat flatter. Yeah.
I remember some other studies, I have to go back, that indicate that including the LCVDs was a major improvement.
Yeah. Well, if you think about EPPS, they only have D mesons, right? They don't have quarkonia. So maybe that's what you mean.
So it's the relative,
It's the relative impact. Yeah, we are the only ones that have quarkonia. Right, the A dependence. This basically shows you that as you go from beryllium to lead in the low X region, you can see the increase of shadowing for larger nuclei. And
You said that was based on the log, it goes on log of A equals.
right, exactly.
That makes a lot of sense for the EMC region, but I think makes much less sense in the shadowing region, where A to the 1/3 seems more likely.
Yeah.
Have you considered,
Well, basically, we have. I mean, in the past we had a different A dependence, right? As I showed. In the past we had this dependence, but basically, we've discussed this also with colleagues. When you do an expansion, you can more or less match one to the other if you go beyond the leading log and you go to log squared. So it's not in the end, it doesn't make such a big difference.
Partly because you don't have any intermediate A data.
Yes, right. But of course, I mean, the A dependence. If you have more different nuclei, then you can say more. Yeah. Very good remarks. I'm very happy to be here. From all sides, that's really great. Okay, so
I'm sorry, while you're there,
Okay.
So how much would you benefit from more nuclei in the EMC effect region? Or would it not add too much because you have sort of those two parameters?
I mean, it would still be interesting, I think. Let me postpone that question to the very last slides when I talk about short-range correlations. Okay, because that's where the focus is. Okay, but to finish the discussion on the CTEC 25 release, because the crystal ball parametric fitting of the quarkonium has not so much of a theoretical basis, even though we showed it was consistent with NRQCD and open heavy quark production at next to leading order. We decided to do a dedicated fit, nevertheless, to open heavy quark data only in the full NLO framework with a variable flavor number scheme. And to do this, we had to desymmetrize the. Okay, these are technical details. So maybe I shouldn't say too much again. You need fragmentation functions then, because these heavy quarks hadronize. You have to grid the code to make it fast. We optimize the scales again because the uncertainty otherwise is too large. We optimize the scales in proton-proton, and then we take these scales and fit the nuclear data. And when we do this, we obtain again a very good chi-squared. This fit has 500 data points less because it does not include the quarkonium. It only has the open heavy quark. But in the end, the result is very consistent between the data-driven approach and the NLO PQCD approach. So in particular for the gluon, there's basically no difference. So this is a sort of an alternative fit, or will be an alternative fit to our main fit. Okay, so let me get to the conclusion and then a short outlook. So nuclear PDFs, they are based on the factorization theorem, perturbed evolution, theoretical treatment of higher twist effects and deuteron and target mass effects in high X, for example. We have these different effects that we would like to understand. There are theoretical models for some of them, but we take in principle, like in this business, a model agnostic approach, and then later we will try to determine what the underlying physics is. Okay, I mean, something that's also, of course, very important, where we've written one paper, but this was not included in the talk, is to look at nonlinear effects, to include recombination of partons in the evolution, and see, eventually see if this can be seen in the data, and you would expect an enhancement in nuclear collisions, and then, of course, try to relate that to the CGC and initial state phase transition. Yeah, so I've discussed the corrections for high X data, the problems with the neutrino data, and the importance of this for the strange quark, and then I focused on the LHC data with the different processes and their sensitivities. First indications that we need to go to next to leading order. And yeah, so something that I haven't really mentioned, but which will be discussed also at INT next week, and some of you are working on that, is the alternative way of determining PDFs not from fitting data, but from first principle calculations in non-perturbative QC on the lattice. Here, the difficulty is that, well, the recent advance is that previously the lattice people could only fit moments of PDFs, whereas now they can determine X-dependent pseudo or quasi-PDFs, which are related to the real PDFs by some integral transforms. And the problem for nuclear PDFs in particular is that the results are so far restricted to the large X region and low A region. So I think maybe A equals 4 is the maximum that they can do. Everything heavier is not yet possible. And so they have focused on particular quantities that are relevant, like U minus D ratios and momentum distributions. So our new fit NCDEC25 is a new global analysis which combines all the previous ones that I have mentioned in passing with their particular sensitivities. Here you can find the references again if you want to look them up. And I have discussed the differences with respect to our 10-year-old previous fit. And so this is now the updated global comparison with our competitors again. So, and here now you can in particular see that NCDEC25 has the lowest gluon uncertainty and has a very competitive strange quark uncertainty also with, when compared to EPPS and NPDF. So we think this will be a very good and hopefully long-standing result. We will see. Something which I haven't been able to discuss in this talk, which was meant to be more of a review and with some recent results, is an alternative approach, which has received quite some attention last year. And so the approach that I've taken so far is to look just at the modification of quarks and gluons in a single nucleon. So in a sort of a mean field approach, how the nucleon is modified when it's sitting in the larger nucleus. However, we know that this mean field approach has its drawbacks, and the short-range correlations of two nucleons play an important role in nuclear binding. And so in this paper, which was published in PRL, we've taken the approach together with MIT experimentalists and to actually modify the ansatz at the starting scale to take into account both a single nucleon and a per-nucleon pair. And so this actually produced very interesting results. And as I told you, I was discussing this for a full day with people there. Just to give you a flavor of what the result is, this is the fraction of protons bound in two nucleon pairs as a function of the nuclear mass number. And surprisingly, the increase with nuclear mass comes out exactly the same when you fit deep elastic scattering data as when you fit quasi-elastic scattering data at low energies. And pretty much the same as you obtain from theoretical calculations on quantum Monte Carlos. So this was quite unexpected and seems to corroborate the idea that these correlated nucleons are a substantial fraction of the nuclear binding story. And what's also interesting is when you look at the quark and distributions, or here it's really the structure functions. What you see is that the modification of the structure function at high x in the EMC region is universal. So it does not depend on the nucleus. So basically all the nuclear information is contained in the fractions, and the quark modification or the momentum shift in the role that the valence quarks play in the binding is the same. So this was quite an interesting result, and with this I would like to conclude this talk. Thank you very much.
Thank you. All right. You come.
Yes, I think when you are answering to a question, you said something like local momentum conservation in the PDF.
Yeah.
Like, does it mean, like, for example, you can get the particle distribution of a box inside of the, I don't know, like, what would you mean?
Yeah, okay. I don't remember exactly the details. I would have to look up the Strickmann-Gouze paper again.
Okay.
But you can also look it up. It's about anti-shadowing and by Gouze and Strickmann. They describe exactly this local momentum concept.
And then another question is, like, I heard something about intrinsic charm.
Ah, yes.
And then, like,
Yeah, I mean, Stan Brodsky has been advocating this for decades, right? So, yes, that's another interesting question. So this would be a higher Fock state in the nucleon. There has been some claim about evidence for intrinsic charm in protons, which is debated, I would say. Yeah. And the question is, of course, also, is it also okay if you see the nuclei? And the way to go, I think, is to look at charm plus Z production, for example, in LHC data. So, of course, in Terra, you have this F2 charm structure function, which this evidence, claimed evidence was based on. But now we have the LHC, which is a precision machine. So I think one should look at C plus Z as a specific property of intrinsic charm.
Sure.
Yeah, so since you have this one up, so one way to interpret this is sort of, as you said, that it's modification of the bound deuteron, if you like, compared to the free proton or neutron. But you'd get essentially an indistinguishable result if you still treated as just the individual nucleon modification, but had it scaled with the number of short-range correlations, with the idea of using essentially correlations as measuring the average density the nucleons see, and then putting that into a more conventional EMC effect. Mm-hmm. And quantitatively, the fact that there's a flavor-dependent modification here is tiny compared to the uncertainties in the data. Mm-hmm. But it does, whichever way you look at it, it also raises the issue of with beryllium, because that was kind of the original nucleus that showed this big difference. Using that A-dependent parameterization for beryllium in particular might not be very good, even if it works for a wide range of nuclei. Mm-hmm. And we hope that we are in the process of adding a bunch of other light nuclei for which it may not work as well, but hopefully that's useful.
Thank you.
So I lost a little track about the quark versus charm, but I mean LHC goes down to 10 to the minus 4, maybe 10 to the minus 5. You're also plotting 10 to the minus 5. You get good fits to the data. Your gluon density on your last slide just keeps on going up. There's no sense of it falling over at 10 to the minus 4, 10 to the minus 5. Is there any room, or let me try to ask a question to answer. How constraining is this on any, and my understanding is it's a linear framework. How constraining is this on any nonlinear evolution effect? Can we start putting limits on that?
Yeah.
And kind of what do we, what remains for new experiments and new colliders to actually look for?
Yeah. For this, I would have to change and look up the paper that I wrote with Buddy. I think then I can show you the size of the effect that we would expect for different.
Can I interject my question before you switch screens?
Yeah.
So on the last slide, what went too fast to me. What is universal there? I mean, you had many.
It's a modification. It's a ratio of bound quark or F2. Okay, let me show exactly what it is again.
Yes,
so
okay.
it's proton, also the dinucleon
Yes.
structure function as fitted from
Yes.
the heavy quarks for different heavy nuclei. Sorry, as
Over the
compared to
field.
the isoscalar.
Yes, but you have now many curves, so that doesn't
Yeah.
be very universal to me.
No. Well,
That's where.
so basically, what we have, I didn't show the ansatz. The ansatz has a mean field nucleon
Mhm.
and a short-range correlated parton. And so these many curves are the mean field nucleons.
Mhm.
And they have a spread here,
Yes.
in particular at low x. And this is the modified correlated.
And that's the same everywhere.
And that's the same.
Okay, now I got it. Thank you.
Right.
Now you can show him. It is blood.
Okay, so let me show you the paper with Vladimir. And that was actually a bachelor student that wrote this paper with us. So third-year student from Berlin. That was quite impressive. So this is okay. This is including nonlinear effects in this ansatz. I mean, it looks pretty similar to what we've discussed earlier. Again, for up to I guess 197 here. So as you go down to 10 to the minus 5, you can see for the quark singlet. Let's see. What should I look at? Yeah, this is the upward evolution, I think. Let's see. So it's going up to gold. Upward evolution from 2 to 10 GeV, right? It's like an 8% or 10% effect. Yeah, at 10 to the minus 5. And it's larger. It's larger, of course, for heavy nuclear than it would be for small nuclear.
All right. Quick
Do
question.
you have results on the U bar and D bar difference?
We do, but I didn't show them.
Tomorrow.
Yeah.
Tomorrow.
You will talk with him tomorrow. You can show him. And then
When you fit to the pillar data, you assume there is no hard medium effect.
Yeah, let me just answer this once more. The CJ collaboration, they have different approaches to D bar over U bar. I think they have D bar over U bar in CJ 15 and D bar minus U bar in CJ 22 or so. But it doesn't really make a big difference in terms of.
Yeah, we'll talk tomorrow.
Yeah.
When you fit to the LHC pillar data, you already assume there is no hard medium effect.
Right.
Or recently, your collectivity in small system observed.
Yeah, it's an important question that always comes up. We haven't included any medium effects. So basically, one measure would be to look at the size of the higher twist effects that we fit, right? And to take that as a measure of final state interactions. Yeah.
all right.
Okay.
Let's thank Michel again. See you down there.